Okay, so quick recap. Last week, we introduced the concept of polynomials. We had all these names. We learned about trinomials and binomials and monomials. We talked about, how those exponents interact with one another. They follow their own list of rules, which we've covered a few times. And we also did our 4 arithmetic operations: addition, subtraction, multiplication, and division, with a variety of polynomials as well. Today, we're going to kind of it's going to feel a lot like the opposite of the multiplication we did last Thursday. So where we either used a box or distributed into our parentheses, we're basically going to take something that has already essentially been distributed into and undistribute. And this all can be boiled down to a term we like to call as factoring. But we've covered factors probably before. In fact, you've probably listed factors for just regular numbers as early as elementary school, where you may have listed factors. Maybe you did what were called factor trees. So factors have been around for a while. Got a question here. The final's on the 18th. Ideally, I'd like to take the final as early as the 16th and leave the 17th and 18th open for makeups if necessary. So if you have everything finished, you'll be done ahead of schedule. All right, so factors. We're going to do a little bit of review for factors of just values, which for our purposes, something's a factor when it can be divided nicely from another number or later expressions. If you ever divide anything and you get a fraction or a decimal, or later we sometimes encounter negative exponents, whatever you just divided by at that point in time was not considered a factor, because dividing by factors give us nice, clean numbers. So what we're going to do here is we're going to look at a list of different values. We're going to list each of their factors. As we get to some of the longer lists, I'm going to show you personally what I do if I'm trying to list factors. And then we will jump into kind of the meat of the lesson today, where we're going to be factoring polynomials. So here is our list of values. Starting with example A, we have the value 4. What are some factors of 4? Numbers that divide nicely from 4.
2.
2. Yep.
1.
1.
4.
And 4. That's all of them. So the number's relatively small. So 2, 1, and 4. And if I list those in numerical order, we have 1, 2, and 4. Now, how do we know we can't look for any larger values than 4, the number itself? Do what? 2's in the middle. Well, 2 wasn't in the middle when you listed it for me. But if you think about it, if you divide a number by any other value larger than itself, you're always going to get a fraction. Because 4 divided by 5, 4 divided by 6, divided by 7, divided by 8. Those are all going to be fractions, which will not divide cleanly. They'll be nice fractions, but they won't divide to be whole numbers. So you can never have a factor larger than the value itself. In fact, every value has itself as a factor, usually paired with 1, because everything can be divided by 1. And this one happened to also have a factor of 2. So that list wasn't terribly exciting because, well, there's only 3 factors of 4. What about 12? 1, 12, 2, 4, 6. There's 1 we jumped over. Miranda's on here. She says 3. So already you kind of starts to feel a little bit overwhelming because we're jumping around and it's kind of hard to keep track of which ones we've listed. But if we were to list them in numerical order, we said 1, 2, 3, 4, 6, and 12 are all considered as factors of 12. So already the 12 is not a terribly big number, but the list is already growing fairly quickly. So that must mean 13, which is even bigger than 12, must have even more factors. What are factors of 13? 1 and 13. What else?
That's it.
That is it. So just because the numbers continue to get larger does not mean that every number has a long list of values.
6 and 7 are close though.
6 and 7 are close to what?
13, like 6. You multiply 6 by 6, that gets you 13. Oh, it gets you 14, I'm sorry. 6, 7, 8, 9, 10, 9, 12, 13.
Are you adding? It sounds like you're adding.
Oh, see, it's the morning. You're right.
So be careful. So factors, when we're thinking about factors, we're thinking about the operations multiplication and division, particularly division. But we want to make sure we don't accidentally compare them using addition and subtraction. Let's go one more, and then I'm going to show you a little trick that I like to use to keep my head on straight when I'm looking for factors. What are some factors of 21? 3, 21, 1,
5,
not quite.
5, 2.
What pairs with that 3? Think of it that way. Miranda's on here. She's got your back. She says 7. So, and we could sit here and think about even more numbers, but just for the sake of time, I'll say, those are all the factors: 1, 3, 7, and 21. But as hopefully we're already noticing is when we're sitting here just trying to list them out, most of us, myself included, will jump around to the ones that come to our minds immediately. But if there isn't some sort of systematic approach, odds are you may accidentally forget 1 or 2 as you skip over them, going to the ones you feel more comfortable with. So for the next one, which is 24, I'd like to show you a method I use that allows me to very carefully make sure I haven't missed any. So off to the right here, I'm going to write the number 24, which is the one that we're looking at. And underneath, I'm going to list factors of 24, but instead of just listing them individually, I'm going to list them as pairs. I'm also going to list them starting from the smallest value I can think of and working my way up very, very systematically, one at a time. If it's not a factor, I skip it and move on to the next. So I'll do the easy one. 1 times 24 is 24. So 1 and 24 are both factors of 24. What about 2? Is 2 a factor of 24? 2 times,
Like 9, I think.
a little bigger. 2 times 12. Okay. What about 3?
Yeah.
3 times
8.
8. What about 4?
5, 6.
4 times 6. What about 5?
No.
No. What about 6?
Yeah.
6 times 3.
Careful.
6 times 4.
We've already listed 6. In fact, as soon as your list begins to go back on itself, right then, at that moment, so long as you've been writing them as pairs, you now know that you have found every single factor. So I don't even have to go any further. As soon as I start to cycle back around, I know that if I were to list them in order, going down the left column first, and then jumping over to the right and going up the right column, I have every factor listed here. So if I were to come back over to my little sample space here, factors of 24 are 1, 2, 3, 4, 6, 8, 12, and 24. There's quite a few numbers, and 24 itself isn't that large of a number, but it just so happens to have several values that are less than it that are also factors. 36 is also going to be one that we want to be careful of as well, because there's probably ones that our brain goes to immediately. Like for me, I think 36, I think 6 times 6 right off the bat. Maybe you think of 9 times 4. But there's actually a lot more hiding in here. And using this approach, kind of like I used over here, is a good way to try to make sure you don't accidentally jump over any. So I'll do the easy one. 1 times 36. What about 2?
Yeah.
Lana's saying yes. Here's a question for you. If you're not sure,
18.
how'd you come up with 18?
I divided it.
Good. If you're ever unsure of whether or not a number is a factor, for 2, you could do 36 divided by 2. And if you get a clean number, in this case, you should get 18, you actually just found 2 factors. Factors always come in pairs. What about 3?
Yeah. Times 13.
Close, really close. 3 times 12. What about 4?
Yeah.
4 times.
I kind of messed up, but.
If you're not sure, take 36 divided by 4.
I want to say it's 12.
9.
You get 9.
Yeah.
What about 5? No. 6?
6 times 6.
6 times 6. 7? 8?
No.
No. 9?
Yeah.
Well, of course, it's already on our list. In fact, because of the way I had to write 6 times 6, I already am starting to cycle back again. So at that point, I could say, well, I must have listed all the factors of 36. And now I know that I don't have to go all the way back to 36 again. I've already covered everything because I've written them in pairs. So the factors of 36 are 1, 2, 3, 4, 6, 9, 12, 18, and 36. Now, yes, very easily I could go on Google and say, hey, Google, what are factors of 36? And already my phone's trying to do it. It's panicking.
Here's the top YouTube result.
So yes, I could do a quick Google and find list of factors. Now I'll give you, I know we got 2 more here, but here's to ease some of your discomfort. Tomorrow, I will actually give you a full sheet of paper that lists all the factor pairs for the values 1 to 100. So instead of trying to reinvent the wheel, I'll give you the first 100 sets of factor pairs. Now, if I ever give you a number larger than 100, well, then you're going to want to go through, maybe grab a calculator and say if I said 173, you do 173 divided by 1, divided by 2, divided by 3, until you get a factor pair list that starts to cycle back, and then you'd be good as well. But again, I will give you the first 100 starting tomorrow. What about these last 2? 49. What are factors of 49? 7 and 7. There's also the obvious one.
1 and 49.
1 and 49. And those are, in fact, all of them. So 1, 7, and 49 are the only 3 numbers you could divide 49 by evenly. And then on this last one, and I always admit to my errors. For the longest time, I don't know why, I always thought 51 was prime, and I never took the time to check it. It's not actually. 51 actually has more factors than 1 in itself. Well, it's not even, so 2 wouldn't be a factor.
It's like 13579.
Do what?
Like 13579.
Right, so 13579, so it's an odd number. Odd numbers do not divide nicely by 2. It does divide by 3, however. 3 times what? 3 times 17. So the factors of 51 are 1, 3, 17, and 51. Now, I've actually already kind of ruined the surprise because I said it already. What types of numbers are numbers which are only divisible by 1 in themselves? Prime numbers. And did we have any prime numbers in our list?
C.
C. So 13 was the only prime number we had. Now, something else I want to point out to you, because a lot of the times I have students think that prime numbers are the same as odd numbers or vice versa. It's not necessarily the case, because look at the last two on our list. 49 is an odd number. It is not prime. 51 is also an odd number, and it is not prime. The 21 is an odd number, and it is not prime. So even ones are the easy ones, because even numbers are always divisible by 2. So you're always going to have at least another pair. Odd numbers are, I would say, are the trickier ones, because sometimes we think, oh, it's not divisible by anything. It's not always the case. So like I said, doing this by hand takes a while. So I will give you the first 100, because you will use factors quite a bit going forward as we finish up this last unit we go through. Now, taking this idea of factors and then introducing them into the polynomials we introduced last week, we can then do something that is actually undoing what we've been doing all along. I used the word doing way too many times there. So basically, if you recall, since unit 1, if I gave you a set of parentheses, what did you want to do? Distribute. We're going to do the exact opposite. And instead of taking something and multiplying it into a set of parentheses, we're going to take a long expression and we're going to divide something out of everything and set it back out in front. Bring the parentheses back. Now, right now, it's like, why are we doing this? We spent so much time distributing. I promise you there's a reason. It helps us solve these new equations we're going to introduce on Wednesday. And it allows us to do some more manipulations than we initially could. So it says here that polynomials can be broken down into smaller parts by using factoring. So we've been listing factors at least. Factoring polynomials can be imagined as undoing multiplication or reverse distribution or undistributing, however you want to informally describe it. So anytime we're factoring polynomials, we're going to want to check for what is called the greatest common factor first. So we're going to spend a couple days factoring, but anytime we factor, we're going to check for what's called the greatest common factor first. I typically abbreviate it with GCF because otherwise it's a mouthful. But greatest common factors are the largest factor, hence the word greatest, that can be divided nicely, which is the word factor, from all the terms, which is where the word common comes in, from our polynomial. So if I were to break down this statement, largest factor, that's where the word greatest comes from, can be divided nicely, is how we describe the word factor. All the terms, that's where the word common comes from. So yes, it's a little bit out of order when written that way, but we're looking for the greatest common factor, the absolute largest thing we can divide out of all the terms nicely. Now, below we have some expressions, polynomial expressions, where we're going to factor out the greatest common factor from each. There is a hint here, however, that is suggesting we use division to pull it out. So we're going to see this in action. So starting with the first one. Now, right off the bat, you'll notice hey, Josh, there's variables here now, unlike the list of values we're looking at up above. That's okay. We're going to pick those apart too here in just a moment. But first, let's use our words to describe what we have here. What is this? Well, we're looking for a number that's divisible from each of these, but this has two terms.
Is it an expression or no?
It is an expression. Yes, technically that's true. But if it has two terms, it's a word we introduced last Thursday.
Binomial?
It's a binomial. And if we wanted to go one step further, the highest exponent is a 2. So technically, this is a quadratic binomial. Again, don't worry too much about that extra flair on it. But it is a binomial, which means it has two terms that when we decide what we're divided by, it has to satisfy both terms. So what I like to do, because the hint was to use division, is I like to put a little division bar underneath every single term. And then instead of trying to think of something that works for everything all at once, I go through and think about the smaller parts. So I always like to start with the coefficients. So the coefficients we have here is a 25 and a 10. What is the largest factor that they have in common? I would say 5, because if you listed them out, 25 has factors of 1, 5, 25. 10 has factors 1, 2, 5, and 10. The only two they have in common are 1 and 5. We want the largest. So the largest thing you could divide both of these values by is a 5. That takes care of the coefficients. But in comes the variable. So when we pick apart the term greatest common factor, common means we want something that they all have in common, and we want the most that they have in common. So in terms of the variable x, at most, how many do they have in common? 1. Anyone else agree, disagree? Well, how many x's are being multiplied in the first term?
2.
There are 2. How many x's are being multiplied in the second term?
1.
Only 1. What is the most I could take out of both?
1.
1. So Leanna was right. Because so I see Miranda said that there are a total of 3 x's, but we're trying to think about what they have in common. So imagine for just a moment if our first term was Johnny and our second term was Sally, and instead of x's, they have apples. Johnny has 2 apples, Sally has 1 apple. If I wanted to take the same amount of apples from everybody has to give me an apple, because Sally can't give me more than 1 apple because 1 is all she has. Now that's not fair for Sally because obviously she's going to be out, but we're taking the same amount from every single one. Since this first term has 2 and the second term only has 1, you can't take more than what the smallest one has. So they both can give up at most 1x. So 5 takes care of the coefficients. The x takes care of the variables. What we found without really dwelling on it too much is this 5x is my greatest common factor. Now, it's very important I don't lose this greatest common factor. So the first thing I usually write down when factoring an expression like this is the greatest common factor. But here's where that reverse distribution comes in. I'm actually putting in a set of parentheses because I'm now going to divide each term by this greatest common factor of 5x that we've decided upon. So I like to do it in little chunks. 25 divided by 5 is 5. X to the second divided by x is just x, because remember, if you're dividing common bases, you subtract their exponents. So you have 2, you take 1 away, you still have 1 left over. What about negative 10 divided by 5? negative 2, and x divided by x,
None.
technically they're gone because we had one, we took one away, there's no x's left over. And just like that, we have factored this binomial. Now, how could I check real quick that this is in fact?
Could we just distribute?
You could imagine what would happen if you distribute. 5x times 5x would give you 25x squared. 5x times negative 2 should give you a negative 10x. We have it, again, we're not solving anything yet because notice the one thing we haven't introduced yet in this unit is the equal sign. So we're not solving anything. We're merely changing the appearance using our operations. Now, our operations very uniquely here are being used to do a process called factoring, but basically all we're doing is taking an expression and changing how it looks. Now we can essentially do it both ways because on Thursday, I gave you an expression like this and you distributed using multiplication. Today, I'm giving you where you ended on Thursday and said, let's go backwards and let's figure out what was being multiplied to make that expression. So I think it was the first week I used this, but in order to be a good car mechanic, you can't just be able to take it apart. You have to be able to put it back together. And in math, you really need to know how to work these processes forwards and backwards. So let's take a look at the second example. What type of polynomial is this? Monomial, binomial, trinomial? What's that? A binomial. So that means we have two terms to consider. I'm going to set up two little fraction bars here, ready for that division. And I'm going to start with the coefficients. One of them is just a constant, so it is its own coefficient. 6 and 8. Largest number you can divide both 6 and 8.
2.
2. Miranda's on here in the chat agreeing with you. I would agree as well. 2 is the largest value you could divide both 6 and 8. Okay. Then we move on to the variables. How many variables can I take from both? None?
Because 6 doesn't have an A.
You mean I can't take something from nothing?
Nothing.
If there's no A's here, I can't take an A. And if I can't take an A from one of the terms, I can't take an A from any of the terms because whatever I'm dividing by has to be consistent throughout all of them. So here, it's not as terribly interesting, but here, our greatest common factor is just a 2. So I'm going to write it down. I'm going to write my parentheses, and then I'm going to divide to see just what was inside the parentheses before this imaginary distribution had taken place. 6 divided by 2 gives me a 3. 8 divided by 2
4.
gives me a 4. And a squared divided by, well, is there any common base being divided by a? So what do I do with a squared?
You bring it down.
Bring it on down. If you didn't touch it, if you didn't move it, didn't lose it, bring it along. If you're worried that you've missed something, do it. You can either do it on the paper or you can just do it in your head. Imagine what do you get if you distribute a 2 back into the parentheses. If it's what you started with, then what you did must have been correct. Again, don't hesitate to stop me if you're like, whoa, Josh, where'd that number come from? Because there's a lot of pieces involved, but if you imagine them as just little bitty divisions all through this process, hopefully you can track where each of these values come from. Okay. Try to complicate things here just a little bit. What type of polynomial do we have here? It's another binomial. So even though the first term's negative, again, let's not worry too much about that. We're really just worried about how many terms we need to divide everything by. So Miranda's already ahead of my next question, which is awesome. If you look at the coefficients, negative 20 and positive 25, the largest value we can divide out of those is going to be a 5. But then we move to the variables. How many x's can they both give away?
2.
2. Why not more? The first one has 3.
Because they're not equals.
Well, they don't necessarily have to be set equal, but does this second one have 3 to give?
No.
So if it can't give 3 away, I can at most give away 2. So that means 5 will take care of the coefficients. X to the power of 2 will take care of the variables. We find our greatest common factor of 5x squared. We set it aside before we divide. So negative 20 divided by 5 will give me a negative 4. X to the third divided by x to the second would be just an x. Technically, if you wanted to see x to the power of 1, it's the same. We usually hide the ones. 25 divided by 5 gives me a 5. And x to the second divided by x to the second, they're gone. There was 2 there. We took 2 away. So the second term doesn't have any more variables. And yet again, there we are. This is the factored form of that binomial expression we started with. If you're wanting to check, try out the distribution. You should get back to where we started. Questions so far? Now, so far, everything we've looked at have been binomials. And the way I like to think about it is if I was at home and a friend came over and we're like, hey, I'm hungry. What are we going to go get to eat? 2 people, it's usually pretty easy to figure out something that both people agree upon. But if you throw in a third person or a fourth person or a fifth or sixth or a whole group of people, the more people you have in the mix, the harder it becomes to find something that everybody is very happy about. That kind of becomes the truth with these expressions. So you'll notice, hopefully, that this next example is a trinomial, which means it's not enough to just please 2 of them. We need something that makes all 3 of them happy so that we can divide it nicely. As before, I usually recommend starting with the coefficients. So Miranda's on it again. She says 5 would probably work. I would agree. 5 divides nicely from 5, 20, and 10. And obviously 5 can't have a factor any larger than itself. So I know right off the bat that 5, I certainly can't go any larger than 5. What about the variables? How many can I take?
2.
2. Because this one has at least 2. This one has at least 2. Uh-oh.
1 then.
Oh, this one has at least 1?
Yeah.
Where?
No, it has none.
It has none. So even though these 2 terms have x's to give, because of that first term, it ruins it for everything. So I can't take away any x's if that first term has no x's to give. So unfortunately, this one's not terribly interesting because my greatest common factor here appears to only be a 5. But every greatest common factor is important. So set the greatest common factor to the side before you divide. 5 divided by 5 is going to give us 1.
5
Oh, fine, fine. I think it's 10 divided by 5. I'm like, oh.
Negative 20 divided by 5
-4.
is going to give me a negative 4. What happens to the x to the 7th?
You bring it down.
Bring it down. I didn't take any x's away, so it's still x to the 7th. 10 divided by 5
2.
is a 2. And what happens to the x to the 2nd?
Bring it down.
bring it down as well. And just like that, it's factored.
Kind of easy, honestly.
Once you get the hang of it, it's not too bad. But what I start to see when someone gets too comfortable is that they don't write down what they're dividing by, or at least they don't write the exact same thing down under every single one. And then they make mistakes. Mistakes that they would have otherwise known better not to make if they saw it written down. But sometimes laziness makes us goofy. So I got the second one up there. I realized I know it's a little bit too late. I've been going through these rather quickly. I haven't been giving my online students a chance to write them down first before we actually do anything with them. So give you guys a quick preview there. The rest of you, if you want to start thinking about what we're going to be dividing by, that's good too. Okay, well, first off, how many terms do we have?
3.
There are 3. This is a trinomial. So we want to make sure that whatever we decide works nicely for all 3 terms. So Toby, you said 2. Seems good to me. 2 would make all the coefficients happy, and 2 can't have a factor bigger than itself. So I would say 2 would be good for the coefficients. But then what about the variables?
A to the second.
A to the second? And why is that? What made you choose A to the
Because
second?
they all have 2 in them.
Wrong.
They all have 2 in
You
them.
can take 2 from 3.
I know, this one.
So this one has at least 2 to give.
3 has 2 to give.
Has at least 2 to give.
12A has 2 to give.
This one has exactly 2 to give. Can't give any more than 2, in fact. So I would say that you're absolutely right. It only has 2 to give, which means that's the most we can take from all of them. So with a little bit of thought process, we come to the conclusion that our greatest common factor for this one is 2a to the power of 2, which again, I set aside before I go through and divide. 10 divided by 2 is going to give me 5. A to the 4th divided by A to the 2nd
A to the second.
should be A to the 2nd. We had 4, we took away only 2. What about 2 divided by 2? Positive 1, and you said just an A. So there was 3 there. We took 2 away, which just leaves us with an A. And then 12 divided by 2
6.
gives me 6. A to the 2nd divided by A to the 2nd,
Kansas.
they're gone. There was 2 A's there. We took 2 A's away. There's no more variable on that last term. And again, remember, if you're ever uncertain, if you think that maybe you've forgotten something, misplaced something, think to yourself, what would I get if I were to redistribute, if I were to multiply in this 2a to the 2nd? If you don't get the original statement, go back, double check your division, double check your steps before moving on. So there's the last one here on this page. Give you guys a chance to jot it down. So the last one is a trinomial as well. So we have to satisfy all 3 terms. And again, starting with the coefficients, what's the largest value you could divide all 3 coefficients by?
3.
3. I would agree. So 3 is going to work for all 3 coefficients. How many variables M can we take away?
Just 1.
Why just 1?
Because that's all one of them has left to give.
Are you focusing on the last term here?
Yes.
So the very, very last term only has 1 M to give. So although the other ones have more, we can't take any more than what the smallest amount has. So at most, we can only take an m away from each of the variables. So this time, our greatest common factor is a 3m. So I set it aside, then divide. 3 divided by 3 is going to give me
1.
3, what?
1 dividing.
Yes.
That's why I put the fraction bars in there. M to the fourth divided by m
M to the 3rd.
will give us m to the third because we're only taking 1 away. 15 divided by 3
5.
gives me a 5. M to the third divided by m,
M to the 2nd.
we're taking 1 away from everything. Because remember,
I thought we were taking 2, I'm sorry, my bad.
Oh.
I thought we were on the last one.
so I'm glad you said that though, because Toby, this is the exact reason why I harp on people. Make sure you're writing it down underneath each. That way you can visibly look and say, oh, 15 divided by 3, 5. M to the third divided by m, taking 1 away, m to the second. I'm a very visual person. I have to see it so I don't get lost. What about this last term?
1.
Just 1?
Yes.
What happens to the variable?
It cancels.
Good. The variable there's only 1. We took it away. This is what we're left with. So in terms of complexity, technically all we're using here is division. Now, because we have to satisfy multiple terms, we can't just divide the biggest thing that works for the first term and hope it works for the rest. We do have to consider every single term. It does take a little bit of thought. You have to pause for a moment, decide what you can divide by before going through, and actually doing it. So what's interesting though, maybe I think it's interesting, is the solutions we ended up with are the exact things that you started with last Thursday. On the assignment, I had some monomials times binomials. I had some monomials times trinomials. So we essentially can work these problems now, or at least these types of problems, both forwards and backwards, technically. Any questions on just basic greatest common factors?
If A, B, and C.
Well, I can come back to those in just a moment. So I'll bring those back. So if there's no questions on finding greatest common factors or what to do with them once you find them, what I'm going to do then is introduce you to a new process called factor by grouping that allows us to use the idea of greatest common factors in a slightly more creative manner. So as it says there, and I've kind of alluded to it earlier with coming up with ideas for dinner with multiple people, often when you start to get to 4 or more terms with polynomials, it becomes less likely that you're going to find a greatest common factor that satisfies all of them. And probably, because we're only going to look at 4 terms together, probably the most frustrating thing, at least for me personally, is when I have something that divides nicely out of 3 of the terms, but then I get to the 4th term and it doesn't work. And so it doesn't work at all. So factoring by grouping, what it essentially allows me to do is split the polynomial into groups, hence the grouping. Because we may be able to factor using greatest common factors more than once. Now, factor by grouping, you're going to tell about halfway through this process whether or not it's going to work. And I'll show you what I mean once it occurs. But right off the bat, how many terms does this polynomial have? 4. So we would just lump it into the blanket term polynomial. Can you think for all 4 coefficients of a number that would divide nicely out of all of them? There's usually one particular number that students fall on first.
2.
Well, 2
6.
2 looks like it might work because they're all even except this one. So 2 unfortunately will not work for the 49. Surprise, 2's not the one I usually hear. I usually hear 7 because 7 goes into 42 6 times. 7 goes into 49 7 times. Bless you. 7 goes into 28 4 times, but unfortunately, 7 doesn't go into 24. So we could sit here for a while and get really close and say, oh, it worked for these 3, but it doesn't work for the 4th. And we'll get frustrated very quickly. So to set that aside, to save you that frustration, I will tell you that there is no greatest common factor that will work for all 4. You might get as close as 3, but there's nothing that works for all 4. So grouping, what we do is, assuming it's written in descending order already, as this one is, because sometimes we have to shift things around. What I like to do is cut it right down the middle. The first 2 terms on the left, the second 2 terms on the right. Notice that the subtraction sign, I went ahead and kept it with the value 24, because you can't just have a subtraction sign chilling out by itself. It needs to be attached to something. So what I've done now is I've split it into 2 groups. And what I need you to do for just a moment is imagine, as we're focusing on the left here, imagine that the right side's not there right now. I want everyone to imagine with me that we're just looking at a binomial, 42x to the 3rd minus 49x to the 2nd. What is the greatest common factor of these 2 terms? Start with the coefficients, 42 and 49.
There are none.
I said there was one.
7.
7.
Okay.
And do they have any variables in common? X to the 2nd. So again, if you're still looking at the 2 terms on the right, this kind of feels wrong because obviously 7x to the 2nd would not work with either of those for their own reason. But again, I'm pretending like that side is not over there. I'm just factoring this binomial on the left. And we came up with the greatest common factor of 7x to the 2nd, which I write down as I've done with all the greatest common factors today. And then in parentheses, we're going to write what we're left with when we do this division. So 42 divided by 7 gives me a 6. X to the 3rd divided by x to the 2nd, just an x. Negative 49 divided by 7 is a negative 7. And x to the 2nd divided by x to the 2nd is gone. So I have successfully factored that binomial. Okay, so we're going to put that one on hold. I'm going to say, okay, let's look at the second binomial on the other side of this little wall we put in here. What is something you could divide out nicely from negative 24x and positive 28? 2 would work. I think there's a larger one though. 12 would work for 24, unfortunately would not work for 28. So a little bit smaller now. So between 2 and 12.
4.
4 would work. Can I take any variables out with it?
No.
Why not?
Because there's only 1x.
There's only 1x on the 24. The 28 has none to give. Now, I will say real quick, if you are writing in pen, I would pause for a moment because I'm going to make a minor adjustment here in just a second. If you're writing in pencil, stick with me because we can erase. That's what the eraser's for. So we're going to say that we're taking out a positive 4 for my greatest common factor, which we set there to the side, and we go through and we divide. Negative 24 divided by 4 is a negative 6. What happens to the x?
Bring it down.
Bring it down. 28 divided by 4
7.
is 7. Now, I'm going to pause there for a moment, and I'd like to hear your thoughts, or what do you observe?
They're the same. They cancel each other out.
What are the same?
The 6x, the negative 6x and the 7, they're like opposite.
The 6x is positive, the 7 is negative.
Okay, we're dancing around. So, Craig, let me hone everybody else in so they're looking at the same things you guys are looking at. It sounds like you're looking at the binomials that are located inside the parentheses. Is that correct?
Yeah.
Now, Leanna, you initially said that they are the same, but Toby, what were you saying?
They're not
They're not quite, because this 6x is
positive.
positive. This one's negative. What about this 7?
It's negative.
And so
But
they have the same pieces.
I thought that's -7.
Well,
Like the-
28 divided by 4,
Wait, on the left, right here.
well, this one is -7.
Oh,
So they're really, really close. Wouldn't it have been nice if they were exactly the same?
Yeah, because it would have been easier just getting it done.
Well, that it would have been aesthetically pleasing, because man, if the parentheses match, that would have been nice. Let me ask you this. What could I have divided by instead that would not affect the values, but would only affect the signs?
Themselves, so 6.
Well, we got the 6, well, the negative 6 from negative 24 divided by 4. What if I wanted a positive 6? What would I have had to divide by here?
And negative 4.
A negative 4?
Positive.
Well, we did divide by a
Right,
positive
divided
4.
by a negative divided by a negative is a positive.
Yeah, okay.
Now, if we're talking greatest common factors, it has to be the same for both. Is that correct?
Yes.
So that means down here, our greatest common factor is instead a negative 4. And when I do that division, negative 24x divided by negative 4 gives me a positive 6x. 28 divided by negative 4 gives me a negative 7. And now, fortunately, the binomials are identical. So I'm going to make a little note here. We know that grouping is working when everything in the parentheses is identical. So we know that grouping is working when everything in the parentheses is identical. So for these two greatest common factors that we removed and set to the side, what we were left in both cases was a 6x minus 7. So nothing we've done so far has been that far out of the ordinary, because it was just factoring greatest common factors. Here's where it gets a little weird, but it still uses the same concept. Imagine with me for a moment that this is still a problem that we have split in half. So we have the factoring from the left binomial, and what we have factored from the right binomial. What do they both have in common? What is the same? What's in the parentheses? The 6x minus 7. They have the same binomial. Well, when we were talking about greatest common factors, at no point did I say that a greatest common factor always has to be a monomial. The greatest common factor can be literally anything that they both or all have in common. Well, in this case, both halves here have in common this binomial 6x minus 7. And just like any other greatest common factor, I can divide it away. Now, if you think about where we usually put greatest common factors, we usually write them down first before we do the division. Now, the division initially seems intimidating until you think about the fact that earlier when we did like x divided by x, we said it's gone. X squared divided by x squared, they're gone. Well, 6x minus 7 divided by 6x minus 7 eliminates, leaving me with 7x to the second from the first half. When I divide out the 6x minus 7, 6x minus 7 from the 6x minus 7 from the second half, they eliminate, leaving me with just a minus 4. And just like that, it is factored. Now, it seems strange because it's new, but one of the best things to do if you're ever uncertain of something is to see if you can take what you end with and kind of reverse engineer it or work it back to where you started. So I'm going to show you on this first one. This is not something I require on the assignment, nor will I do it for the rest of the examples here together with you. But if I wanted to check this really quickly, I would say, imagine for a moment that this was what I gave you, a binomial times a binomial. So I'm going to check by multiplying them back together again. And if you recall from Thursday, I personally, if you learned FOIL, great. I personally like to stick with a box because it comes out really nice and neat. So I'm going to write the binomial 6x minus 7 down the left-hand side here to list my, or excuse me, to identify my rows. Then I'm going to take the 7x squared minus 4 and use those to list or name my columns. And then one by one, just like I had you guys do last Thursday, we're going to fill in each of these squares by multiplying whichever row we're in by whichever column we're in. So the top left corner, 6x times 7x squared gives me start with the easy part. 6 times 7 should give me a 42. X times x to the second, when you're multiplying common bases, you add their exponents, so you should get 42x to the power of 3. Then I move to the right, 6x times negative 4 should give me a negative 24x. Moving down to the second row, negative 7 times 7x to the second gives me negative 49x to the second. And the last one here, negative 7 times negative 4 gives me a positive 28. Now, unlike the ones from last week, do we have any like terms inside our box? No, because this one's x to the third, x to the second, x, no variable whatsoever. So if I was to write these out in descending order, I would have 42x to the third minus 49x to the second minus 24x, and then the positive 28. Notice anything about it? Let me zoom out a little bit more.
It's the same equation
Not equation,
for all.
expression.
Yeah.
No equal sign, so it's an expression. It's the exact same thing we started with. Exact. And the reason for that is we were able to initially, the factoring breaks things apart. What we did on Thursday allowed us to put things back together again. So we can take a polynomial, break it down into two binomials that are being multiplied together, or vice versa. We could take two binomials, multiply them together to get a polynomial. We can essentially work this problem forwards and backwards, which means it opens up doors that otherwise we couldn't have worked through. So I have three more here for you. We'll go a little bit faster just to kind of see the routine, because once you see it, it's almost like you can't unsee it. So for the sake of time, I'll spoil a bit of the surprise and I'll tell you that there's nothing you can divide out of all four terms. So we will want to group them. I'm going to split mine in half here. And I'm going to focus on the left half first. 7x to the third and 6x to the second.
I have a question, Josh.
Yes,
Do
go right
you
ahead.
always split them right down the middle?
What's that?
Do you always split like it just split it right down the middle? Like you have 7x and 6x on one side and then the other one's on the other side?
I typically do if it's already in descending order. What I wouldn't want to do is split it into a group of 1 and 3, because then there's no way I'd get a matching binomial later on. What you'll encounter is there's two hidden problems on the assignment today where the terms are actually written in a scrambled order, and you'll have to adjust. 9 times out of 10, or at least the ones that I give you, usually cutting it down the middle will be sufficient.
But putting it in that descending order is what we'll have
Descending
to.
order is going to make it a whole lot more likely that it'll work in your favor.
Okay, cool. Thank you.
You're welcome. So Miranda's asking, can we rewrite it? Yeah, absolutely. If it's ever in an order that's not favoring this method, I can write these four terms in any order I wish, so long as I keep the signs with the terms that they started with. So like these two terms would have to be negative no matter where they fell in that order. These two terms would have to be positive. So absolutely, you can rewrite the order any way you wish. Descending is typically will work though. So if it's not in descending order, writing it in descending order could get you over that block. So taking a look at these first two terms here, starting with the coefficients, what's the largest thing you can divide 7 and 6 by? 1, which that's kind of a bummer. Kind of feels like nothing's going to change, but thankfully we can probably do something with the variables. How many x's can we remove from both? 2. So the coefficients aren't going to do much, but we can take away an x to the power of 2 from each. So my greatest common factor here will be 1 x to the second. And as I go through and divide, 7 divided by 1 stays 7, but x to the third divided by x to the second leaves me with just an x. Moving to the second term, 6 divided by 1 leaves me with 6, and x to the second divided by x to the second is gone. So this is what I get when I partially factor the left-hand side. Putting that on hold, moving over to the right-hand side, we now have negative 42x and negative 36. What divides nicely from both 42 and 36? I would say 6 would work. Now, knowing that sometimes the signs get a little bit wonky, I'm going to check something real quick. Right now, if I were to divide negative 42x by positive 6, I would get a negative 7x. I'm really hoping it's a positive. So instead of keeping it a positive 6, we could instead divide by a negative 6, and hopefully that'll adjust both the signs to my favor. So on the second side here, -6 is going to be my greatest common factor. -42x divided by -6 will give me a positive 7x. -36 divided by -6 will give me a positive 6. And I'm happy because the binomials are what's in the parentheses matches. So to take it one step further, we say that if that's the case, then these two halves technically have a greatest common factor of 7x plus 6. And as with any greatest common factor, you usually write it to the side before you divide. But the division itself, all it's really doing is removing the binomial from the first half and from the second half. And what we're left with is going to give us our remaining binomial. So we have the greatest common factor 7x plus 6. And then beside that, we have the remaining 1x squared minus 6. So again, I'm not going to require you to check like I did for the first one, but know that if you want that extra exercise, if you want that practice, if you're just kind of concerned, it's on the table and it's just not required. Moving to the next one. Obviously, I got to pick up the difficulty just a little bit here. You'll notice I've thrown in some extra variables. Initially, that causes panic until I remember I'm really just looking for what they have in common. But again, to save us some time, I will tell you that there's nothing you can divide out of all 4 terms. So I am going to split it in half again to group it into smaller chunks that I can then work with. I'm going to start on the left-hand side. So what is the greatest common factor first of our coefficients, 12 and 16? 4. Okay. And then I work my way through the variables. Can I take any x's away from both?
Yes.
How many?
1.
Just 1, because the first term there only has 1 to give. What about that y? Why can I not take a y away?
Because only one has a Y.
Only this one has a y. This one has none to give. So you can't take away something that's not there. So my greatest common factor for the first half is going to be 4x. Set it aside before you divide. When you divide, you get 12 divided by 4, which leaves you with 3. X divided by x, it's gone. What happens to the y?
It moves down.
It just slides on down. If you didn't take it away, it's still there. -16 divided by 4.
-4
It's going to give me a -4. And x to the second divided by x
is an X.
leaves me with just 1x remaining. So 4x is the greatest common factor. Inside, we have 3y minus 4x left over. Then we slide on over to the second half here. 3 and 4, greatest common factor of 1. Can I take anything else away? Do they have anything else in common? A p? Just 1?
Just 1 P.
Okay. So with a greatest common factor of 1p, dividing it out here, 3 divided by 1 is 3. P divided by p,
Nothing.
it's gone. The y, well, we didn't touch it, so it just comes on down. -4 divided by 1 gives me a -4. P divided by p, it's gone also. The x just falls on down. And although it felt a little strange at first, I can have some comfort in the fact that when I look at these two halves now, I know I'm on the right track because even though they're a little bit unique, they both have the same binomial 3y minus 4x, which can then be treated as my big greatest common factor, which I set aside before I divide. And by divide, I really just mean remove it from the first half, remove it from the second half, and what's remaining produces my second binomial, 4x plus 1p. So even when there's a lot of pieces in there, just again, systematic, little by little, work things through and know that there's a, halfway through this process here, if your binomials inside the parentheses match, you could say, I'm on the right track. If they don't match, that tells you don't try to push forward. Go back, double check what you divided out of the two halves, adjust, see if you can correct any mistake you may encounter. Last one, also a little bit busy. I'll give you guys a couple seconds here to jot it down. I'm going to go ahead and put my little split there in the middle, and then we'll start here in just a moment. So in the first half here, 15ab minus 21a to the fourth. Let's start with those coefficients. 15 and 21 both have a greatest common factor of 3.
I'll say 5.
Well, 5 would work for the 15. Unfortunately, the 21 would not work. Because if it was 20, we'd be set. 21, unfortunately, doesn't work. Anything else they have in common?
A,
Just exactly 1a?
just 1A.
Okay. Is that our greatest common factor then?
Yeah.
So 3a is our GCF for the first half here. Set it aside before I divide. 15 divided by 3 is going to give me a 5. A divided by a, it's gone. B, well, I didn't divide by any other b's, so it's still there. Negative 21 divided by 3 gives me a negative 7. A to the fourth divided by a
A to the third.
will give me an a to the third. We're only taking one of them away. So that factors the first half. Then I transition over here to the second half. Starting with the coefficients, negative 20 and 28.
2.
2 would work. It's a common factor. It's just not the greatest.
4, -4.
Okay, well, you said 4 first, and then you said -4. What made you think maybe you need to change the sign here?
That's the positive 5.
Because you want a positive 5b?
Yeah.
So right now, negative 20 divided by 4 would give you a negative 5. So you were thinking ahead, which is awesome. It saves you some backtrack. So changing the signs here just means we divide by a -4 instead of a positive 4. Negative 20b divided by -4 is going to give me a positive 5b. And 28a to the third divided by -4 is going to give me a negative 7a to the third. And again, even though it looks a little bit strange, I know that I'm on the right track because everything in the parentheses matches for the two halves. So my final greatest common factor here is the binomial 5b minus 7a to the third, which I set aside before I divide. And in this case, that binomial divided by itself just eliminates it from both halves. And I get my second binomial from whatever's left over. And in this case, we get 3a minus 4. And that's it. Technically, we only really just used one concept today, and that concept is greatest common factor. Now, grouping, a little bit more advanced, but it really just has you using greatest common factors a total of 1, 2, 3 times. Still basically the same concept though, just a little more advanced.